students, welcome back with new lesson in physics grade 9. We will continue studying thermal properties or thermal physics. Now, today we will study thermal properties, heat capacity and specific heat capacity. We take a small note about it in the last lesson, but now we'll take the mathematical formula to calculating the specific heat capacity and amount of heat and heat. Thermal properties of matter: when object absorb heat, we use the symbol Q, capital Q, to refer to amount of heat that absorbed inside the object. There T rises. T, it means temperature. When object releases loss quantity of heat, their temperature decreases. Different materials undergo different delta T. Delta T, it means change in temperature, may be raise up or down, for some heat absorbed or released. Thermal capacity C equal amount of energy or amount of heat needed to raise a body's temperature 1 degree. Water has high heat capacity, takes lots of energy to change its T. We said before that water has high specific heat capacity. Metals have low capacities. A little heat energy gives a lot of delta T. It means a little amount of heat give us large difference in temperature, but this is for metals. But in water with high specific capacity, more energy or great amount of energy just give or just make little difference in temperature. Why? Temperature is measure of average kinetic energy. Kinetic energy for molecules or tiny particles of which composes the matter. Of particles, 1 kilogram of different materials contain different of particles. Kinetic energy must be spread over varying numbers of particles. Weights of particles, it takes more energy to move heavier particles. Bond strengths, some materials have particles that are easy to move. So this it means the last one, bond strengths, some materials have particles that easy to move. It means the specific heat capacity depend on the composition of the material. Some materials have strong bonds. It means the particles can't move easily, but some materials it has weak bonds. It means the particles it's easy to move, so it need little energy to raise up its temperature. And also the heavier particles need more energy to move it faster, but little particles or lighter weight particles need a little energy to move it. Why does water have such a high heat capacity? Because its composition, water, and this is metal. This is the composition of water and this is the composition of metal. Water molecules form strong intermolecular bonds with each other. The metals have weak intermolecular bonds. As we see in the figures, the water has a strong intermolecular bond. This is oxygen and hydrogen, 2 atoms of hydrogen. This is a strong bond, and also the particles, these molecules and other molecules bonded or have a strong intermolecular bond. But in metals we have free electrons and we have weak intermolecular bond than water. Thermal capacity equal amount of heat Q needed to raise an object temperature 1 Celsius. C equal delta Q over delta T. Delta Q it means change in heat energy divided by change in temperature. Its units, joule per Celsius. Q equals C multiply delta T. Q energy in joules and delta T temperature change in Celsius or Kelvin. But temperature scale, we use it in gases law, we must use Kelvin scale. Example 1. If the thermal capacity of water is 5000 joule per Celsius, how much heat is required to raise its temperatures from 20 to 100 Celsius? So, we'll start writing the formula Q equals C delta T and substituting by the given information. Q equals 5000 joule per Celsius. This is capacity, yes, this is thermal capacity, and delta T 100 minus 20 equal 80 equal Q 400 kilojoule. So we need 400 kilojoule to raise up water from 20 to 100 Celsius. This is for 1 gram only of water. Another example. How much heat is lost from a block of metals of C equal 800 joule per second when it cools from 60 to 20 Celsius? So it will lost energy, so the temperature will decrease. Heat capacity vest. If we have, this is nil metals, small C or small specific capacity. This is a big metals, a large C. So heat capacity depend on the mass of the object. A specific heat capacity C includes term for mass of materials, amount of energy required to raise temperatures of 1 kilogram mass of substances 1 Celsius or Kelvin. C equal Q over M delta T. M equal mass in kilogram. C specific heat constant joule per kilogram. Delta T equal Tf over minus Ti. Tf T final, the final temperature, and Ti the initial temperature. So delta T may be positive or negative according to loss or gain energy. Q equal MC delta T. Q is the energy in joule. Delta T is positive if substances absorb energy and negative if for E release energy. Specific heat. Some substances, specific heats of selected materials like aluminum, it's easy to heat up because its specific heat capacity is low. Water, why hard to heat? Because it have high specific heat capacity. Exercise 3. A 45 gram piece of aluminum is heated from 25 to 55 Celsius. How much energy is required? Now we have a difference raise up, so it gain energy and a mass of aluminum, and we need the required energy to raise up the temperature from 25 to 55. By using the specific heat capacity of aluminum, we can calculate energy. At first we put the formula Q equal mc delta T. After that Q equal, substituting by mass and specific heat capacity of aluminum from the table, and delta T, the difference in temperature, 55 minus 25, it's positive. We can say C equal 1200 joule. Another exercise, the specific heat capacity of water is 4200 joule per kilogram C Celsius. How much heat will be required to raise the temperatures of 300 gram of from 20 to 60 Celsius? This experiment methods to determine specific heat capacity. We use calorimeters, mixed substances using sterling waters, observe temperature change, use conservative energy to calculate the specific heat capacity. This is a calorimeters. These calorimeters consist of these isolated materials or non-conducting materials, covers of wood to prevent transmission energy from to outside. This sterling rod to stir the metal fragment inside the waters to have the same temperatures. This is water. Thermometers to calculate the change in temperature. Mixing substances obeys E conservation. Q lost by one substance equal Q gained by another. It means minus lost, take a negative sign. Loss, it means MC delta T1 equal MC delta T2, or MC delta T1 equal MC delta T2. Delta T1 a change in the material which lost energy. A delta T2 it means the change in temperature in the materials that gain energy. Throw hot metal into cold waters, then Q lost by metals equal Q gained by water. Hot metals and cold water. Inside the calorimeter we will measure the difference in temperatures for solid with a known specific heat, liquid with known specific heat. We know the specific heat of water, but we didn't know the specific heat of solid. 0.05 kilogram metals pulp is heated to an unknown temperature. So the initial temperatures for the metal, I don't know it. It is then dropped into a calorimeter containing 0.15 kilogram of waters of 21 Celsius. The pulp and the water reach the final temperatures of 25. So the final temperatures of water equal final temperatures of the metal equal 25. Initial temperatures of water is 21, but the initial temperatures of the metal pulp we don't know it. If the specific heat of metals is 999 joule per kilogram Celsius, find the initial temperatures of the metal. And also we know the specific heat capacity for the water by substituting in the relation MC delta T1 equal MC delta T2 and calculate the final temperatures. It will be equal 81 Celsius. Heating coil in liquid. How can we use energy conservations to find C specific heat for liquid? We use this equipment, or we use this device. This is a calorimeter and this is thermometer. This is the power supply for the coil to heat up the water, and this is joule meter. joule meters. This device calculate the amount of electrical energy that used to heat up the water. Electric energy lost by a coil equal energy gained by a liquid. Electric energy equal VIT equal MC delta T. V is the potential difference, I current, and T equal time, plus the cup, but we neglect the energy that absorbed by the cup. A heating coil with voltage potential of 6 volt and current 3 ampere is immersed in 7 kilogram of water. How long will it take to heat the water from 20 Celsius to 35 Celsius? Assume the cup absorbs no heat. It equals about 2442 seconds. By using the last formula, this formula VIT will substituting by V equals 6, I equals 3, T this is a known variable, so I will calculate it. By substituting M we know it, C of water we know it, and the difference also we know it. Substituting by M, C and delta T and VI, we can calculate T equal, which equal 2442 second by minute equal 41. Phase states of matter. Phase states, it means change from solid to liquid, from liquid to gas. This is each state we call it a phase. The kinetic particle theory of matter. This is liquid, this is solid, this is gas. From the pattern of the particles we can know the phases of the materials. All matter is composed of small particles, atoms, molecules, or ions. They are in constant random motions. The particles are so small they can be treated as if they are points or no volume. This is a comparison between phases properties: solid, proximity, energy, motion, volume, shape. Solid is closed, energy little, motion vibrational, volume is defined and defined shape also. Liquid is closed, energy moderate, and motion rational, and volume defined but shape undefined. Gas is far apart, a lot, energy, translational motion, and indefined volume, also indefined shape. Energy, it means the average kinetic energy for the molecules. We know that solids, its motion is very little, short range of motion, so it has a little kinetic energy, but liquid, it's more freely than solid, so has moderate energy. But gas, the particles can move faster in any direction, so it has a lot of energy. This is, we know that how we can change solid to liquid and liquid to gas: cool, heat, and cool or compress. By compressing gas or cool it, we will change to liquid, and by heat or reduce the pressure, we change the liquids to gas. Total disorders, much empty spaces. Particles have complete freedom of motions. Particles far apart. Disordered particles or clusters of particles are free to move relative to each other's particles close together. Ordered arrangement, particles are essentially in fixed positions, particles close together. No fixed shape, minimal intermolecular forces, no fixed shape, strong intermolecular forces, fixed shape, very strong intermolecular forces. This is a comparison between the three phases of matter. Molecular distance and motion. The molecular distance, solid, vibration only, close together, vibration and close together. This is some rotation, vibrations and transition motion of particles and further apart. But gas, mainly translation is made from space to change its location very far apart. Amount of energy, amount of heat absorbed, phases change, vaporizations, liquid to vapor, melting solid to liquid, substance, sublimations, solid to vapor. This is absorbed energy, but Q released by phases change, condensations, vapor to liquid, it lost energy, and fusion, liquid to solid, and also depositions, vapor to solid. Heat and phases change. When substances absorb or lose heat energy, the temperature change until it reaches a critical temperature. T stops change, substances undergoes phase change. So when we heat up some substances, solid substances, its temperature will raise up, and at a certain temperature it will be fixed for some times and change its phase from solid to liquid. This is the temperature, this is a critical temperature. We call it phase change. Gain loss of additional heat energy results in the phase transformation of matter from one phase to another. When the temperature is fixed for some times, we take this energy to just change the phases from solid to liquid or from liquid to gas without changing its temperature. Substances absorb energy to break molecules bond. Chemical potential energy increases. Average kinetic energy doesn't change. It means we use some energy to break down the bonds molecules. So chemical potential energy increase, but kinetic energy doesn't change. Consider melting. As heat is absorbed, T goes up, particles vibrate more. The kinetic energy increases. At the melting point, particles vibrate enough to slip from their fixed positions, breaking intermolecular bonds. More and more particles break solid bonds until all are slipping past each other in the liquid phases. The potential energy of the systems increases, but the average kinetic energy stays constant at the melting ice boiling points or steam. We will take another conception called latent heat. Latent heat is a physical property that describes how much energy is required to transform the mass of a substance from one phase to another. Latent heat of fusion, heat absorbed during melting or released during freezing. Latent heat of vaporization, heat absorbed during vaporization, released during condensation. So for every change in the phases, we have a latent heat for the same materials. So for liquid, for water, like water, latent heat of fusion to change the water from solid to liquid. Latent heat of vaporization for change the water from liquid to vapor, or the opposite way from vapor to liquid, and also from solid to liquid or from liquid to solid, have the same latent heat of fusion and latent heat of vaporization. Latent heat describes heat energy gained or lost to mass of substances M that undergoes a phase change is Q equal M multiply L. M the mass in kilogram, Q energy absorbed or released in joule, L latent heat, the SI unit in system international units are joule per kilogram. Latent heat for fusion and latent heat for vaporizations for all metals. How much energy is released cooling 10 grams of water from stem at 133 Celsius to liquid at 53 Celsius. This is the specific heat for stem and the specific heat for water. This is latent heat vaporizations of water. Amount of heat to cool stem 133 to 100. We use this formula. And the quantity of heat to condense at 100 Celsius, we use this formula MLV. Q, or amount of heat energy to cool liquid from 100 to 53, we use this formula also. But in this we use C, specific heat for stem, and change in energy temperatures for stem, and in this we use specific capacity for water and the change in the temperature of water. To cool stem, we by substituting in the three formula, to cool stem we have 633 joule, and to condense 100 Celsius, to condense at 100 Celsius, we have 2.26 multiplied 10 power 4 joule, and to cool water we have 1967 joule. Total energy equal 2.52 multiplied 10 power 4 joule by adding all to them. Exercise 2. How much energy is released when 1.5 kilogram of water's vapor at 100 Celsius is placed in freezer and converted to ice at -7 Celsius? Specific heat for ice equal 2.1 multiplied 10 power 3 kilojoule, joule per Kelvin, kilogram. We notice that we use Kelvin, not Celsius here, and this is we use Celsius, so we must change or must make transformation from Celsius to Kelvin. And C, specific heat for water equal 4.2 multiply 10 power 3 joule per Kelvin, kilogram. Latent heat of fusion 3.34 multiply 10 power 5 joule per kilogram. Latent heat of vaporization equal 22.5 multiply 10 power 5 joule per kilogram. So the answer it will be 4.5 multiply 10 power 6 joule by using the previous formula. Heating curves show temperatures change in absorbed energy for substances. This is a curve show the change in temperatures with adding heat energy. At first we will start to raise up, after that it will be constant at this region, after sometimes it will start to raise up and constant in this region and start to raise up. This is fixed region, we call it a latent heat, or the energy absorbed to change the material from phase to another phase. This is from solid to liquid, and this is from liquid to gas. At this, the slope of this portion of the graph q equal mc delta t. Delta t, the slope, we know that the slope equal delta t over delta q. Delta t over delta q, it means delta t over delta q, it will be 1 over mc. The slope of this region, it will be equal 1 over mc, because the slope of this portion equal delta t over delta q from this formula, so the slope is 1 over mc. By these lessons we finished our course, and we will start in revision for a previous lesson, inshallah. Thank you, goodbye.